Geotechnical engineering is the branch of civil engineering concerned with the engineering behavior of earth materials. Geotechnical engineering is important in civil engineering, but also has applications in military, mining, petroleum and other engineering disciplines that are concerned with construction occurring on the surface or within the ground. Geotechnical engineering uses principles of soil mechanics and rock mechanics to investigate subsurface conditions and materials, determine the relevant physical, mechanical and chemical properties of these materials, evaluate stability of natural slopes and man-made soil deposits, assess risks posed by site conditions, design earthworks and structural foundations, and monitor site conditions. Earthwork and foundation construction. A typical geotechnical engineering project begins with a review of project needs to define the required material properties. Then follows a site investigation of soil, rock, fault distribution and bedrock properties on and below an area of interest to determine their engineering properties, including how they will interact with, on or in a proposed construction. Site investigations are needed to gain an understanding of the area in or on which the engineering will take place. Investigations can include the assessment of the risk to humans, property and the environment from natural hazards such as earthquakes, landslides, sinkholes, soil liquefaction, debris flows and rock falls. A geotechnical engineer then determines and designs the type of foundations, earthworks, and/or pavement subgrades required for the intended man-made structures to be built. Foundations are designed and constructed for structures of various sizes, such as high-rise buildings, bridges, medium to large commercial buildings, and smaller structures where the soil conditions do not allow code-based design. Foundations built for above-ground structures include shallow and deep foundations. Retaining structures include earth-filled dams and retaining walls. Earthworks include embankments, tunnels, dikes and levees, channels, reservoirs, deposition of hazardous waste and sanitary landfills. Geotechnical engineering is also related to coastal and ocean engineering. Coastal engineering can involve the design and construction of wharves, marinas, and jetties. Ocean engineering can involve foundation and anchor systems for offshore structures such as oil platforms. The fields of geotechnical engineering and engineering geology are closely related, and have large areas of overlap. However, the field of geotechnical engineering is a specialty of engineering, where the field of engineering geology is a specialty of geology. History. Humans have historically used soil as a material for flood control, irrigation purposes, burial sites, building foundations, and as construction material for buildings. First activities were linked to irrigation and flood control, as demonstrated by traces of dikes, dams, and canals dating back to at least 2000 BCE that were found in ancient Egypt, ancient Mesopotamia and the Fertile Crescent, as well as around the early settlements of Mohenjo-Daro and Harappa in the Indus Valley. As the cities expanded, structures were erected supported by formalized foundations. Ancient Greeks notably constructed pad footings and strip and raft foundations. Until the 18th century, however, no theoretical basis for soil design had been developed and the discipline was more of an art than a science, relying on past experience. Several foundation-related engineering problems, such as the Leaning Tower of Pisa, prompted scientists to begin taking a more scientific-based approach to examining the subsurface. The earliest advances occurred in the development of earth pressure theories for the construction of retaining walls. A rudimentary soil classification system was also developed based on a material's unit weight, which is no longer considered a good indication of soil type. The application of the principles of mechanics to soils was documented as early as 1773 when Charles Coulomb developed improved methods to determine the earth pressures against military ramparts. Coulomb observed that, at failure, a distinct slip plane would form behind a sliding retaining wall, and he suggested that the maximum shear stress on the slip plane, for design purposes, was the sum of the soil cohesion and friction, whereas the normal stress on the slip plane n is the friction angle of the soil. By combining Coulomb's theory with Christian Otto Moore's 2D stress state, the theory became known as Moore-Coulomb theory. Although it is now recognized that precise determination of cohesion is impossible because it is not a fundamental soil property, the Moore-Coulomb theory is still used in practice today. In the 19th century, Henry Darcy developed what is now known as Darcy's law describing the flow of fluids in porous media. Joseph Boussinesq developed theories of stress distribution in elastic solids that proved useful for estimating stresses at depth in the ground. William Rankine, an engineer and physicist, developed an alternative to Coulomb's earth pressure theory. Albert Atterberg developed the clay consistency indices that are still used today for soil classification. Osborne Reynolds recognized in 1885 that shearing causes volumetric dilation of dense and contraction of loose granular materials. Modern geotechnical engineering is said to have begun in 1925 with the publication of Erdbore Mechanic by Carl Terzaghi. Considered by many to be the father of modern soil mechanics and geotechnical engineering, Terzaghi developed the principle of effective stress, and demonstrated that the shear strength of soil is controlled by effective stress. Terzaghi also developed the framework for theories of bearing capacity of foundations, and the theory for prediction of the rate of settlement of clay layers due to consolidation. In his 1948 book, Donald Taylor recognized that interlocking and dilation of densely packed particles contributed to the peak strength of a soil. The interrelationships between volume change behavior and shearing behavior were all connected via the theory of plasticity using critical state soil mechanics by Roscoe, Schofield, and Roth, with the publication of On the Yielding of Soils in 1958. Critical state soil mechanics is the basis for many contemporary advanced constitutive models describing the behavior of soil. Geotechnical centrifuge modeling is a method of testing physical scale models of geotechnical problems. The use of a centrifuge enhances the similarity of the scale model tests involving soil because the strength and stiffness of soil is very sensitive to the confining pressure. The centrifugal acceleration allows the researcher to obtain large stresses in small physical models. Practicing engineers. Geotechnical engineers are typically graduates of a 4-year civil engineering program and some hold a master's degree. In the USA, geotechnical engineers are typically licensed and regulated as professional engineers in most states. Currently only California and Oregon have licensed geotechnical engineering specialties. The Academy of Geoprofessionals began issuing Diplomate Geotechnical Engineering certification in 2008. State governments will typically license engineers who have graduated from an ABET-accredited school, passed the Fundamentals of Engineering examination, completed several years of work experience under the supervision of a licensed professional engineer, and passed the Professional Engineering examination. Soil mechanics. In geotechnical engineering, soils are considered a three-phase material composed of rock or mineral particles, water and air. The voids of a soil, the spaces in between mineral particles, contain the water and air. The engineering properties of soils are affected by four main factors: the predominant size of the mineral particles, the type of mineral particles, the grain size distribution, and the relative quantities of mineral, water and air present in the soil matrix. Fine particles are defined as particles less than 0.075 mm in diameter. Soil properties. Some of the important properties of soils that are used by geotechnical engineers to analyze site conditions and design earthworks. retaining structures, and foundations are specific weight or unit weight, cumulative weight of the solid particles, water and air of the unit volume of soil. Note that the air phase is often assumed to be weightless. Porosity ratio of the volume of voids in a soil to the total volume of the soil. Porosity is mathematically related to void ratio. The by here E is void ratio and N is porosity void ratio, the ratio of the volume of voids to the volume of solid particles in a soil mass. Void ratio is mathematically related to the porosity by permeability, a measure of the ability of water to flow through the soil. It is expressed in units of velocity. Compressibility, the rate of change of volume with effective stress. If the pores are filled with water, then the water must be squeezed out of the pores to allow volumetric compression of the soil. This process is called consolidation. Shear strength, the maximum shear stress that can be applied in a soil mass without causing shear failure. Atterberg limits, liquid limit, plastic limit, and shrinkage limit. These indices are used for estimation of other engineering properties and for soil classification. Geotechnical investigation. Geotechnical engineers and engineering geologists perform geotechnical investigations to obtain information on the physical properties of soil and rock underlying a site, to design earthworks and foundations for proposed structures, and for repair of distress to earthworks and structures caused by subsurface conditions. A geotechnical investigation will include surface exploration and subsurface exploration of a site. Sometimes, geophysical methods are used to obtain data about sites. Subsurface exploration usually involves in situ testing. In addition, site investigation will often include subsurface sampling and laboratory testing of the soil samples retrieved. The digging of test pits and trenching may also be used to learn about soil conditions at depth. Large diameter borings are rarely used due to safety concerns and expense, but are sometimes used to allow a geologist or engineer to be lowered into the borehole for direct visual and manual examination of the soil and rock. Stratigraphy. A variety of soil samplers exist to meet the needs of different engineering projects. The standard penetration test, which uses a thick-walled split-spoon sampler, is the most common way to collect disturbed samples. Piston samplers, employing a thin-walled tube, are most commonly used for the collection of less disturbed samples. More advanced methods, such as ground freezing and the Sherbrick block sampler, are superior, but even more expensive. Atterberg limits tests, water content measurements, and grain size analysis, for example, may be performed on disturbed samples obtained from thick-walled soil samplers. Properties such as shear strength, stiffness, hydraulic conductivity, and coefficient of consolidation may be significantly altered by sample disturbance. To measure these properties in the laboratory, high-quality sampling is required. Common tests to measure the strength and stiffness include the triaxial shear and unconfined compression test. Surface exploration can include geologic mapping, geophysical methods, and photogrammetry, or it can be as simple as an engineer walking around to observe the physical conditions at the site. Geologic mapping and interpretation of geomorphology is typically completed in consultation with a geologist or engineering geologist. Geophysical exploration is also sometimes used. Geophysical techniques used for subsurface exploration include measurement of seismic waves, surface wave methods or downhole methods, and electromagnetic surveys. Foundations. A building's foundation transmits loads from buildings and other structures to the earth. Geotechnical engineers design foundations based on the load characteristics of the structure and the properties of the soils or bedrock at the site. In general, geotechnical engineers estimate the magnitude and location of the loads to be supported, develop an investigation plan to explore the subsurface, Determine necessary soil parameters through field and lab testing. Design the foundation in the safest and most economical manner. The primary considerations for foundation support are bearing capacity, settlement, and ground movement beneath the foundations. Bearing capacity is the ability of the site's soils to support the loads imposed by buildings or structures. For heavier structures or softer sites, both overall settlement relative to unbuilt areas or neighboring buildings, and differential settlement under a single structure, can be concerns. Of particular concern is settlement which occurs over time, as immediate settlement can usually be compensated for during construction. Ground movement beneath a structure's foundations can occur due to shrinkage or swell of expansive soils due to climatic changes, frost expansion of soil, melting of permafrost, slope instability, or other causes. All these factors must be considered during design of foundations. Many building codes specify basic foundation design parameters for simple conditions, frequently varying by jurisdiction. But such design techniques are normally limited to certain types of construction and certain types of sites, and are frequently very conservative. In areas of shallow bedrock, most foundations may bear directly on bedrock. In other areas, the soil may provide sufficient strength for the support of structures. In areas of deeper bedrock with soft overlying soils, deep foundations are used to support structures directly on the bedrock. In areas where bedrock is not economically available, stiff bearing layers are used to support deep foundations instead. Shallow foundations are a type of foundation that transfers building load to the very near the surface, rather than to a subsurface layer. Shallow foundations typically have a depth-to-width ratio of less than 1. Footings are structural elements which transfer structural loads to the ground by direct aerial contact. Footings can be isolated footings for point or column loads, or strip footings for wall or other long loads. Footings are normally constructed from reinforced concrete cast directly onto the soil, and are typically embedded into the ground to penetrate through the zone of frost movement or to obtain additional bearing capacity. Slab foundations. A variant on spread footings is to have the entire structure bear on a single slab of concrete underlying the entire area of the structure. Slabs must be thick enough to provide sufficient rigidity to spread the bearing loads somewhat uniformly, and to minimize differential settlement across the foundation. In some cases, flexure is allowed and the building is constructed to tolerate small movements of the foundation instead. For small structures, like single-family houses, the slab may be less than 300 mm thick. For larger structures, the foundation slab may be several meters thick. Slab foundations can be either slab-on-grade foundations or embedded foundations, typically in buildings with basements. Slab-on-grade foundations must be designed to allow for potential ground movement due to changing soil conditions. Deep foundations are used for structures or heavy loads when shallow foundations cannot provide adequate capacity due to size and structural limitations. They may also be used to transfer building loads past weak or compressible soil layers. While shallow foundations rely solely on the bearing capacity of the soil beneath them, deep foundations can rely on end-bearing resistance, frictional resistance along their length, or both in developing the required capacity. Geotechnical engineers use specialized tools, such as the cone penetration test, to estimate the amount of skin and end-bearing resistance available in the subsurface. There are many types of deep foundations including piles, drilled shafts, caissons, piers, and earth-stabilized columns. Large buildings such as skyscrapers typically require deep foundations. For example, the Jinmao Tower in China uses tubular steel piles about 1 meter driven to a depth of 83.5 meters to support its weight. In buildings that are constructed and found to undergo settlement, underpinning piles can be used to stabilize the existing building. There are 3 ways to place piles for a deep foundation. They can be driven, drilled, or installed by use of an auger. Driven piles are extended to their necessary depths with the application of external energy in the same way a nail is hammered. There are 4 typical hammers used to drive such piles: drop hammers, diesel hammers, hydraulic hammers, and air hammers. Drop hammers simply drop a heavy weight onto the pile to drive it, while diesel hammers use a single-cylinder diesel engine to force piles through the earth. Similarly, hydraulic and air hammers supply energy to piles through hydraulic and air forces. Energy imparted from a hammerhead varies with type of hammer chosen, and can be as high as 1,000,000 foot-pounds for large-scale diesel hammers. A very common hammerhead used in practice. Piles are made of a variety of material including steel, timber, and concrete. Drilled piles are created by first drilling a hole to the appropriate depth, and filling it with concrete. Drilled piles can typically carry more load than driven piles, simply due to a larger diameter pile. The auger method of pile installation is similar to drilled pile installation, but concrete is pumped into the hole as the auger is being removed.